All right, multivariable calculus students, Ms. Deer back on the mic for you today. And we are starting chapter 11 with the idea of vectors. Now, we talked about how vectors have two components. They have magnitude and they have direction. So any two vectors that have the same magnitude and the same direction are equivalent vectors, which is why if I draw a vector here, 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 it doesn't matter if they have the same direction, meaning they're parallel, and they have the same direction, meaning the arrow is going the same way, then they're equivalent vectors. Now, the easiest place to put a vector is what we call standard position, which means that it starts at 0, 0. So all of these vectors are the same, and this vector in standard position looks like this. So do we always put them in standard position? No, and we're going to talk about some cases where it's actually not very helpful. But when you're picturing a vector, we almost always picture them in standard position. Again, where we start, the starting point is called the initial point. Where it ends is called the terminal point. So whenever you have a vector in standard position, because it starts at 0, 0, then we put it in what we call component form, meaning that because it starts at 0, 0, all that matters is where it ends up. So let's say this one looks like it's probably at 1, 1, right here. Now if I had started at a different point, my terminal point would be different. Here, my terminal point would be different. But when we're in standard position and we start at 0, 0, all of these vectors reduce in component form to 1, 1. Now, how do we find the magnitude of a vector? Well, this is just going to be our distance formula, right? The square root of change in x squared plus change in y squared. Now, magnitude is always going to be a positive number. Again, we have a square root here, so we're always talking about something positive. So let's say we have a vector that starts at 1, negative 1, and its terminal point is 3, negative 4. So first, to get this into component form, we want to do where it ends minus where it starts. So 3 minus 1, negative 4 minus negative 1. This is going to give me this vector in standard form. Obviously, I'm not going to leave it like this. We're going to call it 3 minus 1, negative 4 plus 1. So if I were to draw this in the plane, I would start at 0, 0. I would go 2 in the x direction and negative 3 in the y direction. So this would be my vector in standard position. So let's call this vector v. Now whenever we have a vector, it has an arrow above it. You will notice in textbooks that they get a bold. I don't have a bold font when I'm actually writing. So it's really important that you call anything that's a vector, it gets what we call a hat. And it's probably the most important thing we're going to discuss in multivariable calculus and in physics is vector, not a vector. This tells you right away that we're working with a vector. So how would I find the magnitude of this vector v? Well, this is going to be the square root of 2 squared plus negative 3 squared. So this becomes rad 13. So the magnitude of this vector is rad 13. I also want you to start to notice, because we are calculus students, this tells you how far to go in the x direction. This tells you how far to go in the y direction. So when you look at this as a directed line segment, it has a slope of, well, it's going down, so down 3 over 2. Here's your change in y, here's your change in x. All right? Also, I really want you to start to think about how scalars work on vectors. So if I wanted to look at 2v, well, this would be 2 times 2 and 2 times negative 3. I can take the 2 out of here, but I can't get rid of it because what do you notice about this? When I change the vector, I'm going to change the magnitude. And because a vector has both magnitude and direction, although these vectors point in the same direction, they're going to have different magnitudes. This is going to be rad 16 plus 36, which is rad 52. Would I reduce that? Absolutely not. So again, scalars operate on vectors. They also change the vector. What if I wanted to go in the negative direction? Well, then everything is going in the opposite direction. So I would have -2, -3. So these two vectors are parallel. They are collinear when they are in standard position, but these vectors have different directions, so they are different vectors. So this is going to be the foundation of everything that we are going to work with vectors this year.